Hello again. Let me share my screen and we'll move on to section 4.3. Okay, so let's recap for a minute. In section 4.1, we learned that the maxes and mins can be found by putting the first derivative equal to 0 and solving. And then in 4.2, we found that the possible inflection points can be found by finding the second derivative and setting that equal to 0. This third section, we're going to talk about a global max and global min. And global just means like over the course of a certain interval, and they will specify certain intervals. What is the biggest y value? And global minima would mean what is the smallest y value on the whole graph, as opposed to like a local min and max, is where there's a max or min, but it is not the largest one. Okay, so here it is saying what I just said, right? It has a global minimum at some value, right, of x, as long as that value is less than all the other values on the graph, right? Which is basically saying the same thing that I just said. And same thing for a global minimum means it's the biggest y value. It's the biggest y value on the graph, but it occurs at whatever x is, or in this case, p. Okay, so to find the global max and min of a continuous function on an interval, including the endpoints, right? These are the endpoints. Compare values of the function at all critical points in the interval and at the endpoints. Okay, so the first thing that we can say is that, get a pen here, is these 2 points here can be called, they both can be called local mins. Right? And we can also say that these points on this particular interval are, and this one as well, are all local maxes. And let's say that it's over this specific interval. Oops, let me use a different color. Over this specific interval, let's say from this x value of a all the way to this x value, which is b. So we already know what local maxes look like. Now, if we're looking for a global max, we're looking for the highest point on the whole graph. So the highest point on the whole graph is this point, right? So this would be a global max. And the lowest point on the whole graph would be here. So notice that that's called a local minimum, but it's also the global minimum. Okay, now, caveat here is for Wiley, let's say they give you a graph that looks, something like that. And they give you an interval. Let's see, they want you to say from this A value to say this B value. So they're only interested in the endpoint from here to the endpoint here on the graph. So don't just look at the graph, make sure that you look at the interval that they're asking you for, right? So you could say that in that interval, this is going to be your global max. And this right here would be a local max. And in that interval, this point right here would be both a local and a global minimum, because in that interval, even though this goes down and doesn't have a minimum, if they're specifically asking you about a particular interval, make sure you pay attention to that. Okay, so this is going to be your local and global max. So let's say pay attention to interval asked about. Because the global max, local min, all of that could change depending on what interval of the graph that you're looking at. And I say that because I just reviewed all of the problems that I assigned, and they do give you a graph, but they ask you about several different intervals on the same graph, so just be careful. Okay, so what we're going to do is we're going to find global max and min by finding critical points. Okay, so we're going to first find the critical points, and then we'll figure out which one of those critical points is the global max and the global min. All right, so let's start out. Finding the first derivative of this cubic function. This is the same function we've used in the past, I think, right? Maybe not. So we get 3x squared minus 18x minus 48. That's the first derivative. Then we're going to set the first derivative equal to 0 and solve it. Of course, you would, if you factored this, you'd get 3 as a GCF, and then you factor the resulting trinomial to get x plus 2 and x minus 8. From there, you're going to set each factor equal to 0, right? We can ignore 3 since there's not a variable with it. And so that's how we're going to get the solutions or zeros, right? So we have x is equal to -2 and x is equal to 8. So these are the critical points. That's their x values of the critical points. Okay, so now what we're going to do is we're going to evaluate the original function at those two critical points. So if you put 2 into the original function, you're going to get 104 out. And if you put 8 into the original function, you're going to get -396. Now, when they're asking about the interval from -5 to 14, let's just draw that on the graph. So let's say this is -5 and this is 14. You're also going to want to look at the original function at the endpoints of your interval. So we also want to do f of -5 and f of 14. Oops. So if you put -5 in, you're going to get -58 out. And if you put 14 in, you'll get 360 out. All right, so we know that this is the interval between -5 and 14. So if you look at what produces the largest number, that would be f of 14, right? So let's make a scale here that makes sense on our graph. Again, you can use Desmos to graph this as well. So let's say this is 400. This is -400. So what we could do is we could plot the biggest result, which is 360 up here. Let's say it's around there. So this would be an x value of 14 and a y value of 360. And then if we want to graph the local min, the smallest number here occurs at +8, right? You get -396. So let's see if we can scale this right. Here's 8. And then you'd get this point here, which would be 8 and -396. We also get another local min at -5, right? And that would be something, close to, well, probably let's put it right there. So this one would be -5, -58 when we plot it, right? Oops, let me make that legible. And let's see, we also have another local max, which is at -2. And that is what? -2 is 104. Let's say it's somewhere around there. So if you graph this, you would get, and you can graph this on Desmos. Now notice that it goes on, right? If you graph this function, it would go on, but we're only interested in this interval here. So this is going to be your global max. This is going to be your local max. And don't forget that a global max is a type of local max. So if I'm asking you for all the local maxes, you want to include the global max in that too. But if I'm just asking you for the global max, you would only include the highest point. And then of course down here we have the local min and global min. Am I forgetting anything? Oh, and of course this is another local min. Okay, so to rehash, you're going to find the global max and minimum by finding the derivative, setting it equal to 0, which will give you the critical points, and then you're going to evaluate the original function on the critical points and the end points, and plot the points, and you'll be able to see that way. Or you could just graph this. But sometimes these numbers are going to be decimals, though, so you're going to have to know how to do it this way also. Okay, so to find the global max and min of a continuous function on an interval excluding endpoints, or on the entire real line, you're going to find the values of the functions at all of the critical points and sketch a graph. So for example, this particular graph, and this is true in Wiley too, you're going to pretend that it goes off, right? Unless it gives you an actual endpoint, it's going to go off the coordinate plane. So let's label these. This is going to be a local min. Let's see, this is going to be a local max. And this will be your local, or the global min, but also local and global min. But because of the arrows, right? And if we're evaluating this over the entire real line, right? Because there are these arrows, there is no global max. Okay, so that's just you being able to label those points. You should be able to do that with the Wiley problems. Are pretty simple like that. And of course, there could be a graph where there's no global min too, if these arrows were pointing down. Okay, so then they might ask you to like out of multiple choice different graphs. They would ask you to kind of match it up because they can't ask you to sketch a graph in Wiley. Okay, so we want the interval from 0 to 10. All right, so let's start labeling that already. We've got 0. Let's say this is 10. That's our interval we're interested in. Okay. Next, has a local and global max at x is equal to 3. So let's see if this is 5, and this would be like 3 right here. So we want local and global max at 3. So let's put it up here. Oh, shoot, I wanted to do that in a different color so we can follow this. All right, so local and global max at x is equal to 3. And local and global, use a different color. Here. At x is equal to 10. And what else? Oh, and another thing that we know, since they're talking about the interval from 0 to 10, is there's also a local minimum, or it could have been up there, but let's call this local min at 0. You have to include the endpoints. I think I put this. And let's see, what did I forget to do here? Let me look at this again. Local and global max at x is equal to 3. Local and global min at x is equal to 10. Now you got to include 0 in there. All right, so from there, so far those points are going to be on your graph. So you could just simply connect them, or you could add something to it, right? You could, right? So these are the points they told you have to be on your graph, but they didn't say you couldn't put more, right? Let's say you put a local min here. So as long as you have those points on there, there could be more than that on the graph. And notice too that this, if I added that, this right here would be a local max. So you could draw the graph in a lot of different ways, but it has to make that true. Let's see, you know what? I want to redraw this. So it's not quite there. There, because I want the global min to be. So here's another local minimum. I just wanted the global minimum to be clearly the smallest, or the, you know, the y value is the smallest there at 10, because that's what they told us. Okay. Next example. This is kind of putting it all together. So first thing they're asking us for is to find the first and the second derivative. Okay, so the first derivative is equal to 6x squared minus 18x plus 12. And the second derivative is going to equal 12x minus 18. All right, so now it says find the critical points. I'm going to bring this up a little bit. So the critical points, we're going to use the first derivative. So let me use that color again. So the first derivative is 6x squared minus 18x plus 12. We're going to set it equal to 0 and solve for x. Can factor out the GCF of 6 to get x squared minus 3x plus 2. And then factor that trinomial. So let's see, what would be minus 1 and minus 2. Then set each factor equal to 0 and solve that. Okay, so we found the critical points. Now we're going to find inflection points, and that's when we set the, we learned this from section 4.2, that's when we set the second derivative equal to 0 and solve. So 12x minus 18 equals 0. Factor the 6 out, what do we get? 2x minus 3. So 2x minus 3 equals 0. We'll get x is equal to 3 over 2. Or you could think about this as 1.5. Okay, now it says to evaluate f at its critical points and at the endpoints of the given interval, and identify the local and global max and min of f in that interval. Okay, so we've got f of the interval. Let's get the interval in here. Interval is -1/2 to 3. So let's see, where is that on there? Negative, so this would be -1, so -1/2 to 3. That's the interval in which we are interested in. Okay, so -0.5 and 3. So we're going to evaluate on both endpoints in the original function, and you're going to get -7.5 here and 10 here. Then we're also going to evaluate on our critical points And our critical points were 1 and 2. Let's see, we got those with the first derivative, so I'm going to use blue. Okay, and f of 1 ends up being 6, and f of 2 ends up being 5. Okay, so let's graph all those points. Negative 0.5 and negative 7.5. So I'm just going to kind of sketch this in here. So it'd probably be somewhere around there. And then 1/6 would be, let's see, that's over 1 up 6. And then we've got 2/5. So 2/5 would be about here. And 3/10 would be all the way up here. Okay, so let's see what we got. We've got a graph that reads something. Oops, let's draw that a little better. And then we're just going to identify. So let's see, our global max is up here. And our global min is down here, making this a local max. And this a local min. All right, so now let's get to an application of this stuff. See what the graph. I have enough room for that. No, I'm going to bring that down. Okay, so for a time that's greater than or equal to 0 in days, the rate at which photosynthesis takes place in the leaf of a plant, represented by the rate at which oxygen is produced, is approximated by that function. When is photosynthesis occurring the fastest, and what is the rate at that time? So the first thing we're going to do is find the critical points, right? Because if we want to know when the rate of photosynthesis right here, right, over time is the highest, we're looking for a maximum, right? So let's find the critical points first. Using the first derivative. So let's see, derivative of P of T would be equal to, I'm going to leave the 100 on the outside. Remember, it's a constant multiple. And then we're just going to differentiate e to the negative 0.02t. So it would be 0.02 negative 0.02 e to the negative 0.02 t. So that's the first part, that's this part. And remember, I'm using, if you want to find the derivative of e to the kt power, you're going to put k in front and leave the kt here. So that's all I'm doing in that first part. And then if I do the same thing in the next part, I'll just get 0.1 t times e to the negative 1 t. 0.1. There we go. So I'm just differentiating each of those using that rule in both cases. Okay, so then I want to set this equal to 0 and solve it. Okay. So the first thing I'm going to do is get rid of that 100 by dividing both sides by 100. Oh, sorry, this ends up just being 0. So we've got negative 0.02 e to the negative 0.02 t plus 0.1 t e to the negative 0.1 t. Oh, wait, I left something out here. Let's see. First derivative. Yeah, this becomes a plus because a negative times a negative. That's right. Okay. Okay, so let's see. From here, what I'm going to do is I'm going to subtract 0.1 TE and put it on the other side. So I'm going to leave this negative 0.02 E to the negative 0.02 T and subtract negative, or subtract by subtracting it. So it would be negative 0.1 T E to the negative 0.1 T. Decimals are a pain in the butt, aren't they? Okay, and then what I can do, remember I'm trying to solve for T here, but 0.02 and 0.1, what we can do is get rid of what they both have in common, right, by dividing it out. So we can divide this side by negative 0.02 E. Actually, I should do it this way. No, that's fine. E to the negative 1 T, negative 0.1 T. Same thing here. Point 0.02 E to the negative 0.1 T. Okay, so on the left, what happens, and the reason why we're doing this, is that cancels out there, right? And I think I'm missing a negative here. It should be, oh no, it is negative. Okay, so then here I can cancel out this. Oops, I'm gonna use that other color. Oh, and this T, sorry, this should not be here. Okay, so what am I left with? I'm left with oops. On the left side, I'm left with E to the negative 0.02 over E to the negative 0.1 T. Well, there should be a T. And on the right side, after I canceled everything else, I'm just left with negative 0.1. Oh, I got to erase this other T too. There we go. Negative 0.1 all over negative 0.02. Now, if I use the quotient rule for exponents, I can rewrite that side as E to the negative 0.02 T minus a negative 0.1 T. And if I simplify negative 0.1 divided by negative 0.02, I'm going to get the number 5. So if I simplify this, negative 0.02t minus the negative is plus, right? So really it's negative 0.02t plus 0.1t. Gives you e to the 0.08t. Right, and how you solve problems with e is you just take the natural log of both sides. So remember, whenever you have this stuff together, you get to drop the ln altogether, and you're just going to be left with 0.08t is equal to the natural log of 5. And then just solve for t. So we're going to divide both sides by 0.08. And you'll get t, or time, is equal to 20.18. Now, let me read why we're here. Let me read what they're asking you. When is photosynthesis occurring the fastest? Well, it's occurring the fastest in 20.12, or 20.12 days, because that's the max. It's also, notice that there's only one answer instead of two answers. So this is the only critical point. So let's see if it's a max or not. Let's see if I can put it here. So we're going to say is 20.12 the time, 20.12 is 20.12 a max. Well, we can use the second derivative test to do that. So if we found the second derivative using our derivative rules, we would get 100 and 0.004. I'm just using just making it the same rule that I just did. Here, this one here. Just doing it again. I think I'm going to run out of room if I do it here, though. Let me start lower. That's why I did it on my other notes too. Okay, so is t equal 20.12 a max? Okay, so I'm just rewriting this here, minus 0.01 e negative 0.1 t. Okay, so now if we found, we're going to say in the second derivative, let's put 20.12 in. Now it's a max if it's concave down, right? So if we put 20.12 into the original function, what we get out is a negative number. And since it's negative, since the second derivative is negative, we know that it's concave down. And if it's concave down, we know that, you know, it's concave down would be down this way. We know that it would be a max. So the other question they're asking us, so we know it's the max, right? When is photosynthesis occurring the fastest? All right, so we know that this is a max here. Let's say this is 20.12, right? We know that this is the max because we just did the second derivative test on it, right? So if they're asking you when is photosynthesis occurring the fastest, well, this is the rate, right? So the highest Y value here would be at 20.12. And then they say, what is the rate at that time? So they're asking for the Y value. So we know that the X value here is 20.12. They want to know the Y value. So what you're going to do is find in the original function, you want to put that time of 20.12 in to get 53.5. So this is the rate. So you can say that photosynthesis occurs fastest at 20.12 days at a rate of 53.5. So the graph would, if you put that original function in the graph, it would look something like that. A couple more examples. Okay, in this example, the function is given graphically, and the max and min values are, we're going to just read it from the graph. So we already know how to estimate the max and min values from a graph of f, right? You can read off the highest and lowest values. In this example, though, we're going to see how to estimate the minimum value of a quantity from a graph of f against x. So here's what we got. We've got gas consumption in gallons per hour is a function of velocity in miles per hour. So to minimize the gas consumption per mile, not the gas consumption per hour, we're going to minimize the rate here. And we're talking basically about the slope. So I think this will be more clear once we've drawn some pictures here. But if we take the slope of gallons to velocity, we can so here we're taking the average velocity there. So it's y2 minus y1, right? So it'd be 2.5, and I'm just estimating these, minus 0 all over, let's see, what is it? Oh, let's say this is 70. 70 minus 0. So you get 0.04. Let's compare that to gallons and velocity from a different point. Well, actually, I did that in the wrong place. Let me erase this, sorry. That probably didn't make much sense. Okay, so let's take this point right here. So that's the slope that we just found, okay? Well, probably a better estimation might be from a different point of view. Let's say we're doing it from here to here. So if you use those X's and Y values, what we're looking for here is the smallest slope, right? So again, I'm just kind of estimating. And you'll get 0.06. Then let's say we do it from a totally other place, another place here. So here we've got 1.5 minus 0 and 50 minus 0. And this will be 0.03. Okay, so basically what we're trying to do is we're trying to find a velocity that minimizes the slope, right? So if we're trying to minimize the slope, the smallest slope here would be there. So the velocity that minimizes ends up being the X value that goes with that slope. So the velocity that minimizes gallons per velocity would be 50 miles per hour. All right, and one last example. All right, quantity of a drug in the bloodstream T hours after a tablet is swallowed is given in milligrams by this function. How much of the drug is in the bloodstream at time T equals 0? Well, basically, in this problem, all we're doing is finding Q of 0. You put that in your calculator, you're going to get 0, right? And this should make sense because initially there isn't any drug in the bloodstream. Until the drug is given. Until time starts, I guess. Okay. All right, so that's a simple question. When is the maximum quantity of the drug? When is the maximum quantity of the drug in the bloodstream? And what is that maximum? So when is we're trying to find T, right? And then once we find T, we can plug that into the original function to answer that second question. All right, so first thing I'm going to do is, and the first thing I did when I looked at this problem is, let's look what the graph looks like. So if you graphed it, this would be milligrams, and this would be time. And the graph looks something like that, where this is max, right? So the global max would be, the X value of the global max would be the when. And also, you could find a critical point, okay? So if you could put this in Desmos and actually find a whole number, that would be cool, but you're not going to be able to do that. That's why you have to do, you have to set the first derivative equal to 0 in order to find critical point. We already know it's a max, right? Because we saw the graph. But we don't know what, you know, and how many days and all of that. So let's use some calculus here. So if you take the first derivative using that same rule I used on the other example, you would get negative e to the negative t power plus 2 e to the negative 2t. If we set that equal to 0, then the first thing we're going to do is divide both sides by 20. Okay, then we're going to pull 1 to the other side. So let's see. I'll just move over the 2e to the, so I'm going to just subtract 2e to the negative 2t from both sides. So now what I'm going to do is I'm going to divide both sides to try and make it a little simpler. So I'll divide this side by negative 1 e to the negative 2t. And what happens here is the negative, oh, yeah. So this isn't, I think I just did on the opposite sides. Okay. So, oops. Okay. There, I just want you to see that it's the same thing that I'm canceling out. Okay, so I'm canceling out the negative ones here and here. And I'm canceling out e to the negative 2t there and there. Almost done with this problem. So I'm using the exponential rules, right, for quotients where you're going to subtract. So I'd have e to the negative t minus negative 2t. And that's this right side right here. And then if I take negative 2 and divide it by negative 1, I just get 2. And then if I simplify the exponent there, I would just get e, oops, e to the t power, because it'd be negative t plus positive 2t, so you just get 1t. And then from there, we're going to use natural log of both sides. So this is going to go away. You just get t by itself is the natural log of 2. And that is about equal to 0.69 hours. So that's the when, right? And then in order to answer what the maximum actually was, you have to just plug it into the equation. So if you just say Q of 0.69, you end up getting 5 milligrams. Now in this one, you probably could just graph it, right? You'd get a graph that looks like this, use Desmos to zero in and just find the Y value. That would give you the Y value here. And then you could always just plug that Y value into the original equation to find the X value. So don't forget that the stuff that you already know for algebra, when we're doing this graphing stuff, a lot of them you can probably at least check your answer just by using a regular graph. So what happens to the quantity in the long run? So if you follow this graph right here, what happened is that the quantity in your bloodstream is going to go to zero, since eventually the drug wears off, right, and leaves the body. So you could say that the quantity goes to zero. Okay. So depending on what happens next week, I know for sure that Monday you will be using the recorded version of these notes, and I'll also post the notes for you. And we'll see what happens on Wednesday. I might have to be somewhere from my dad on Wednesday. So probably what I'm going to do is pre-record Wednesday's lesson as well, just in case I'm not able to be with you. Now, just because I may miss class on Monday and Wednesday does not mean that we can't meet up if you didn't understand any part of the lesson. So I can definitely, set up a time to meet with you when I know that I'm not going to be with my dad at the hospital. So that's all I have for you for 4.3, and I probably will, like I said, post Wednesday's lesson as well as a video lesson. Thanks, guys. Let's see, stop sharing. And goodbye.